3.8.1, an integrated circuit manufacturer produces wafers that contains 18 chips. Okay. Each chip has a probability of 0.085 of not being correct. Okay. So for part A, find the probability that a wafer contains at least 3 incorrectly placed chips. So probability that x is greater than or equal to 3. Okay. So first of all, you have to go through and you have to say, is this a distribution that we know how to work with? Okay. So for a binomial, you start by asking, do we know in advance how many chips we look at? There are 18. Okay, is the probability constant? Are they independent? And is each one either a yes or no kind of answer? Okay, so this seems to fit everything. So this is going to be binomial. Let me erase that for a second. With n equals 18, p equals 0.085.
Sorry, can you repeat why you say it was binomial?
What?
Can you repeat why you said
Oh, why? So the 3 things for binomial is you have to have in advance the number of trials. And we know that we're only looking at 18 chips. Okay. You have to have your probability of success stay constant for each chip. And they told us that each chip has a probability of 0.085. So this is a constant probability. Okay. And each chip should be independent of the other chips. And it doesn't actually say that specifically, but it does say that each chip has this constant probability, which does kind of imply that they are independent of each other, because otherwise the probabilities would change. And the last condition is that, what, do you remember? It has to be either a success or failure. So only like 2 options. So in this case, we could have correct or incorrect. Although technically incorrects are our successes at the moment. Okay, and so it meets all 4 of those categories or qualifications. Okay, now just in case, so remember, what is the only difference in the qualifications between like binomial and geometric? Which one of these things doesn't hold? Okay, that one is actually still true for the geometric. The only thing that changes for geometric is this fixed sample size. So for the geometric, you don't know in advance how many trials you do. You stop when you get your first success. And the negative binomial is you stop when you get your rth success, so like your 3rd success or 4th success. So you don't know in advance n. So that's the difference between the 3 distributions. Everything else stays the same. So we know it's binomial. Now we're looking for the probability that x is greater than or equal to 3. Now to find this probability, well, what x values are greater than or equal to 3? I would have to do the probability that x equals 3 plus the probability that x equals 4 plus all the way up to the probability that x equals 18. Correct? Is there an easier way that you can think of to do this?
1 minus, go down.
Okay, 1 minus, use the complement rule. So which probabilities do I need? I need 1, 2, and 0. Okay, so for the binomial distribution, 0 is possible because it's possible that they could put 0 incorrect chips. Now when you think about the geometric distribution, you stop when you get your first success. So if you have to get at least 1 success, you have to try at least once. So you only start at 1. For a negative binomial, if you need to get 5 successes, you have to try at least 5 times.
So the only one that includes 0 is the geometric one?
The binomial, yeah. It's the only one that includes our 0. Okay. So at this point, we need to find these probabilities. To do that, it would probably be useful if we remembered the formula for a binomial probability. Okay, for a binomial probability, the probability that x equals k or little x, or whatever you want to do, okay, is n choose k, p to the k, 1 minus p to the n minus k. So remember, this p to the k is the probability of getting k successes. 1 minus p to the n minus k is the probability of getting the n minus k failures. And what does this part do? It's the combination. It counts for the number of ways that I can get that many successes. So we need to do this for each one of those x values. So the first one, n is 18, so we have 18, choose 1 success, times the probability of success is 0.085, and I need 1 success. Then the probability of failure is 1 minus 0.085, and I need, if I have 1 success, I need how many failures? 17. Okay, plus, and now we do everything again for the 2. So 18 choose 2, 0.085 to the power of 2, 1 minus 0.085 to the power of 16. Because if I have 2 successes, I need 16 failures. And we need to do it for the 0. Okay. So it'll be 0.085 to the power of 0, and 1 minus 0.085 to the power of 18. Okay, because I'll need 18 failures. And at this point, I put in my calculator, and it does take a little while, which makes you really appreciate having a normal approximation, and the reason why we want normal approximations. So the 3 probabilities that I get are 0.3379, 0.2668, 0.2021. Okay. Did you guys get those probabilities? So I get that my total probability of 1 minus all of those is 0.193097. Anyone else? .21. Okay. Anyone else get the same thing that I did? Okay. Did you only round to like 4 decimal places, maybe? Did you? Okay, so I got my thing twice, so we'll go with that. Okay, so any questions on this?
It's just kind of using the calculator. Like, what's the difference between NCR and NPR? Like, when
so using the calculator, we have NPR and NCR. Okay, anyone want to answer that question?
Order matters, right?
Okay. So we use this if we have a permutation, which is when order matters. And we use this one if we have a combination, which is when order doesn't matter.
What order exactly? The way that they are.
Yeah, so this is in section 1.7. If you feel like you need to review these, but when we say order doesn't matter, let's talk about Okay, well, let's stick with the same problem. Okay, so if I wanted to have 3 incorrectly placed chips, okay, out of my 18 chips, that could be like, and the first one could be incorrect, the second one could be incorrect, third one incorrect, and then the rest could be correct, 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 etc. Okay, and that would give you 3 incorrectly placed chips. But could I also do an incorrect, correct, correct, incorrect, correct, incorrect, and then all the rest corrects? That would still give me x equals 3. Okay, so when we say order matters or doesn't matter, we say, okay, well, when you're done, when you're counting these, do you count these two things as the same thing? Like, so do you care about the specific order of incorrect, correct, or incorrect, or do you just care that overall there were 3 incorrect chips? Okay, so in this problem, we just want to know if the wafer has 3 incorrect chips. We don't really care which order they were correct or incorrect in. Okay. What is something where the order does matter? Like, can you think of a good example where order would matter? Okay, so like if we're doing a race, first, second, and third place, the order specifically would matter because it makes a difference if it's John, Julie, Stephen, or Stephen, Julie, John, stuff like that. Okay, or if you're picking pins for an ATM. So if I ask you how many possible pins are there for an ATM, 4-digit pins, well, changing the order of your pins, that's going to make a difference. If you punch your pin in the wrong order, does the ATM give you money? Okay, no, and so that's something where order would matter. Okay. But it's just things when you go through and you say, well, is the order I punch the numbers in going to make a difference in this scenario?
So in binomial, now what's it called, binomial?
Binomial distribution.
Does it, do we have any permutations?
Nope. By definition, binomial has to be combinations. Order doesn't matter. If you're ever given a scenario where the order would matter, it wouldn't be a binomial distribution. So the binomial distribution always just counts your successes, so it just counts that there's 3 chips, and it never cares about the order that the chips are in. Okay. Continuing this problem, like B asks, what is the probability that a wafer contains no more than 1 incorrectly placed chip? If we want no more than 1, that means x is less than or equal to 1, which would be the probability that x equals 0 plus the probability that x equals 1. Now, do I need to refine these probabilities? No, we already found these probabilities, right? These two probabilities are, let's see, this one was 0.337948, and the 01 was 0.202106. Correct? Did I transfer those correctly? So 0.540053. Okay. And for C, other things I might ask you is like, what is the expected value? Or what is the mean number of chips? Or what is the expected number of chips? I might ask you anything like that. For the binomial, remember that there's the formula, n times p, which you'll want to have written down somewhere on your sheet. So n is 18, p is what, 0.085? Yep. So 18 times 0.085. So the mean is 1.53. So I expect to get about 1.5 misplaced chips per wafer. Okay. Now obviously on any given wafer you can't have 1.5 incorrectly placed chips, but the average, if I look at many chips, is 1.5 misplaced chips per wafer. Now the problem doesn't ask you for the variance, but I might on the test, I might ask you to tell me the variance or the standard deviation. So the variance is n times p times 1 minus p. So 18 times 0.085 times 1 minus 0.085. So 1.399. So this is what I might ask you to do for the test for the binomial distribution is I'm going to ask you a probability. I'm going to probably ask you the expected value and probably ask you the variance or standard deviation. Now, I will not tell you on the test that it is a binomial distribution. You need to have written down these are the steps for binomial distribution and be able to recognize it.